Sorry, I had to. Yeah, I know. Yeah, you know what? I actually brought that up to my wife this morning. I was like, but I'm sending my Cal 2 students on with 61 problems to do.
There's one class, sir. It's not fair.
Yeah. You can. Hey, but how about you send your parents to come talk to me?
I have an accounting test this week and an accounting final next week, so it's like I'm dying over here.
All right, let's go. I've already wasted 8 minutes. Okay, so last time we talked about the definite integral, right? And we hopefully understand that the definite integral gives us the area between our function and the x-axis. If that function lies above the x-axis, we get a positive number, right? If it's below, it's negative. So with this definite integral, there are some properties that we should be aware of as we move forward. The first property says that if you want to find the area underneath this function f, and you want to look from a to a, that your answer is 0. Does that make sense that that would be the case? Because your interval isn't an interval, it's just a single point, and so you can't have an area. All right? This next one is a little more interesting. The second property says that if you integrate a function between a and b, that if you reverse the limits of integration and you go from b to a, instead of from a to b, that you get the same answer, but it's negative. And that has to do with the fact that, do you remember that the integral, the definite integral, is really a Riemann sum? And the Riemann sum, each of our little widths of our rectangle, right, was, I don't know if you look in your notes, it was b minus a over n. But if we reverse the order, then it becomes a minus b over n, and that becomes a negative number. So all of our widths are negative, and so it just basically changes the sign of the answer. All right, so if you want to reverse the direction of integration, that's fine, but you're going to get a negative answer, or not a negative, opposite answer. Make sense? Sure? All right, this next one, I have a picture. If you integrate a constant function, and I'm using k here for a constant. So if you integrate a constant function, then all it is, the answer is just this. And if you look at what this is, k is the height of the function, because it's a constant function. So it's k high, that's how high it is, right? And then the width of this, that right there, is b minus a. So it's just the area of that rectangle. It's the height times the width. Okay, you don't need to actually do any integration. So let me just do a quick example of this. If you want to integrate from 5 to 10, the constant function 3, it should be what? 15. So it's just that number times the difference of these two. But in all honesty, how hard would that be to actually work out? Like the antiderivative of 3 is 3x, right? And then you plug in 5 and you plug in 10, right? So 10 goes in, you get 30. 5 goes in, you get 15. You subtract, you get 15. So, I mean, it wouldn't have been that bad to do it anyway, but geometrically, you can see what's happening here, why it's this, right? Okay, moving along. We have our fourth property. Now, the fourth property we've seen before. In fact, we've been using it a lot. And that is that if we have a constant next to a function in a definite integral, that the constant can come out. So just like it was with indefinite integrals, we pulled constants out, it still translates over to the definite integral. So that's good. Nothing changes. We can still pull the constants.
I'm sorry, what section is this?
This is still part of the last section, which, remember, I just said I was blending some sections together. Yeah. If you're looking in the book for these properties, I'm not quite sure what page they'd be on.
Okay.
Sorry. Did I scroll down there like that? Oh, sorry, that wasn't supposed to happen. Let me go back to this. Okay, so 5. All right, this one's interesting, but we kind of talked about this already also. If your function is greater than or equal to 0, that would mean that when you graph it, it's above the x-axis. All right, that's what it means for our function to be greater than or equal to 0. You graph it, it's above the x-axis. Then if you find the area underneath it, right, between any 2 points, that you should get a positive area. And then property 6 says if your function is below the x-axis, then your integral is going to give you a negative number, a negative answer. And we saw that, I think I did it with sine, didn't I? With sine we did that. And we said, oh, that area was 1, if you remember, that was 1. But when we did this area all the way from here to here, we got 0. And I said, well, that's because this is negative area. So if the function's above the x-axis, you're going to get a positive area. If it's below the x-axis, you get negative. So that's still something we've looked at already? Yeah? Now, property 7 is one that we're going to use today. And it's pretty important. All right, so let's say we're trying to find this integral here, right? So we're trying to go from A to B. So I'm going to label this A, even though that says 1. I'm going to say A, and here I'm going to say that that's B. Let's say we're trying to go from A to B. This property says that we are allowed to split this up into 2 integrals and add them together. The first integral will go from A to C, and the second integral will go from C to B, where C is any number between the two. So if I pick any number in here, right, like here, and I call that C, then the total area is this area, right, plus this area. And so that integral is that one, and that integral is that one. That makes sense? We're going to use this today. No questions? These properties are pretty straightforward. There's not anything really kind of crazy going on here.
So you said C is a point between A.
It has to be between A and B. Okay. So if you have 2 points and you're trying to find the area under the whole thing, you are allowed to split it into 2 integrals, go from A to any number between A and B, and then continue from that number up to B. But that C has to be between A and B for that to work. All right. We have a test next week, right? Scheduled for Wednesday? So that means, yeah, that's right. I'm going to try and get a review, not a review, but some sort of guide for you together by Friday, and I'll send it out in an email. Now, it might just be like, you know, here's some problems from your homework that I like. You know what I'm saying? But it's not going to be like, here's 12 questions, or, you know, it's going to be more just kind of narrowing your focus a little bit. But I would look at it just as, like, as a safety blanket. It's just there to make you feel better, like you have a review. At the end of the day, the test is over your homework and what we've done in class. All right? I'm not marrying myself to any particular set of problems. All right, next one. Oh, this one's interesting. All right. If f is an even function, then this is true. So we first need to make sure we understand what it means for a function to be even. So let me remind you. F being even means the following. It means that when you plug in x into the function, you get the same answer as when you plug in negative x. I'll give you a specific example of an even function. So as a specific example of an even function, the function x squared, there you go. Right? That's an example of an even function. Because what happens is that when you plug in 1, you get the same answer as when you plug in negative 1. When you plug in 2, you get the same answer as when you plug in negative 2. Right? So when you look at the graphs of even functions, they have a property to them. Right? If you graph them, like if you plug in some value, let's say 1, you get an answer, right? If this is an even function, you get the same answer when you plug in negative 1. So these points are directly across from one another, right? And that works for every point. So it winds up that when you look at the graph of an even function, it is a reflection of itself over the y-axis. All even functions have that property. They are reflections over the y-axis. Now that's important because if we're trying to find an integral from negative a to a, notice that doesn't say a to b, right? it says negative a to a. That means if I'm going to go pick some point over here, negative a, and I'm going to integrate to positive a, that the area under that is equal to twice the area from 0 to a. So what are we using there? I mean, what's going on? What, say it again? Yeah, because of this symmetry, right? Because of the symmetry, instead of trying to find the area from here to here, because these are mirror images, I can just find the area from here to here, right? 0 to a, and then double it, because I have the same thing happening on the other side. All right? Now that property is cool, yeah, whatever, you know? The next one is the one that's really, really nice. It's what happens when you have an odd function. Yeah, so when you have an odd function, what does it mean to be odd? Well, it doesn't mean this, right? Odd is different. It says that when you plug in x and negative x, you don't get the same thing. What you actually get is this. You get negative f of x. So you plug x in, change the sign, and that's the same as what you get when you plug in the negative. So what's a specific example of an odd function? X cubed. Well, it's odd, right? Odd power. Look at this. If I plug in 1, what do I get? 1. But if I plug in negative 1, what do I get? Negative 1. These are not the same, are they? But if I change this to negative f of 1, then that becomes negative. And now they do match, right? So this is what it means to be odd. Now this is a 1414 topic, college algebra. Geometrically, though, here's what it looks like. If I plug in a negative number, let's say I plug in a negative number into this function, it's going to spit out some answer, right? Now, if I take that number and I plug in the positive, I don't get the same answer, do I? I get that answer, but then flipped up, changed to positive. Or if it's positive here, it'll be negative here. And so in terms of symmetry or reflections, what is an odd function? Is it a reflection over the, it's not a reflection over the y-axis, right? Like you don't take this and flip it over, it doesn't land on top of itself. So how could you describe an odd function in terms of reflections? It's called a reflection about the origin, but that really means it's a double reflection. It's both over the y and then the x. Or you could go over the x and then the y. So imagine I reflect this over the y first. Then it would be over here, wouldn't it? And then I reflect that over the x. Now I'm down here. So reflection over the origin is a double reflection. Over y then x. Or you could go over x, right, which would put you here, and then bring that over the y. And then you'd land right on top of this. But in terms of the integral, if we go from negative a to a, right? So from negative a to a, doesn't matter where I go, this area and that area cancel each other out, right? So if they cancel each other out, then the answer is 0, right? Be careful though, I mean, it's got to be from negative a to a, right? If this is not the same number, right, well, opposite in sign, but if this is like negative 2 to 2, the answer is 0, so long as it's an odd function. If it's negative 2 to 4, all bets are off, okay? You have to figure out what the answer is, okay? Questions? So let me give you an example of a problem similar to one that shows up in the homework. So what if we're asked to integrate from negative, let's say 7 to 7 of x over x to the 4th plus 4x squared dx. Now, if you were asked to integrate this, if it was an indefinite integral, so no limits of integration, right? then you would have to figure out what method you're going to use. And what method would you use for that? Partial fractions. You would have to factor the denominator. You'd have to try and get things to match up and hope for the best. But that would be slightly involved, all right? But as I sit here and look at this, I say to myself, well, it's not an indefinite integral, it's a definite integral. And even more, this is -7 to 7, right? They're the same numbers, but they're off by a sign, right? So maybe that property, what is it, property 8 and property 9? Maybe one of those is in play. Maybe this is an, if it's an even function, then I can double the answer from 0 to 7. But if it's an odd function, the answer is 0 with no work, right? No work at all. Don't have to do any integration. So let's check. Is it an odd function or an even function? So the reason I'm doing this is because I want to make sure we know how to do this. All right, so let's check. The function we're looking at here is the function x over x to the 4th plus 4x squared. Okay, is f even? Question mark. All right, well, what do we have to look at? Is f of x equal to f of negative x? Do we get the same answer when we plug x in as we get when we plug in negative x? Is that the same? And this is a question, right? Is that equal? All right, well, let's try this. What's f of x? That. Okay, so f of x is x over x to the 4th plus 4x squared. All right, versus, we're comparing these, f of negative x. So let's plug a negative value or negative x into the function. So if I replace that with negative x, it's just negative x, right? And then if I do negative x to the 4th power, it's negative x to the 4th power, and then plus 4 times negative x squared, right? Now something nice happens here. If you take a negative number and you raise it to the 4th power, the negative is irrelevant now, right? So I could just rewrite this as negative x over still x to the 4th, right? And then this one, because it's squared, the negative doesn't matter, so this is still plus 4x squared. Now on the numerator, it's not being squared or 4th power, right? So it's going to stay negative. So the question is this this?
No.
They are not the same. So is it even? No. Okay. Now does that mean it has to be odd? No, because a function can be even, it can be odd, or it can be neither. You don't have to be one or the other. There's a third option in that it's neither. So now we have to check to see if it's odd. So is f odd? All right, so I'm asking myself, is negative f of x equal to f of negative x? So are these true? Is this true? All right, well, let's look at the left side. What would negative f of x be? Well, that's f of x, right? So if I make it negative, I just need to slap a negative out front. So this one right here, negative f of x, is, I'm going to put the negative out front, but then I'm going to slide it to the top. Is that all right? So that negative that I put out here, I just moved it up. Now that I'm comparing with this, right? And we already did that over here, didn't we? Or is this the same as this? Yeah. They are the same. So it's odd, right? So yes, it's odd. And that means the answer to this is 0. No integration. Yes?
So for a problem like this, would you want to see the word proving that it is odd?
Yeah, if you're going to say straight away that that's 0, you need to show that it's odd. Yep. Sure. That, or you need to do partial fraction decomposition. And if you do that, you should get 0.
And then also, does it matter if either A is negative?
You mean could have been 7 to negative 7? Let me ask you. Should be the same. It would be, remember, if you reverse those, you just change this answer to negative, don't you? Or change the sign. But 0 is 0 positive or negative? Is 0 a positive number or a negative number? It's neither. It's kind of neither and both. It's neither. It's positive means greater than 0, negative means less. So when you put it, if you change the sign of that negative out there, it doesn't change. It's still 0. Now even 0 is an even number, right? 0 is even. It's not positive, it's not negative, but it is an even number. 2, 4, 6, 8, 10, right? Evens actually go both directions forever. So negative 2 is even, negative 4 is even. If you get to a problem in your homework and you see the same number here, just off by a sign, I would start thinking, let's check odd and even first, because the integral might not even be possible. There is a problem in the homework that you can't even integrate it. Like it's not possible for you to do it. Yes?
So if it did come out to be either,
You would have to integrate that. Yeah, but that's not going to happen. Yeah. The whole point of this is to illustrate the property, which is that you can get 0 without doing a drop of work, other than verification. A drop of calculus doesn't need to be done. Okay. All right, I'm going to, just step out for a second, I'm going to give you a problem to work on. We're going to need this problem, we're going to need to solve this problem later, and I don't want to take up class time doing it. So I want you to do this one real quick. I want you to integrate from a to b, x e to the x dx. Now, this is a definite integral, right? So your first step for this is to find the antiderivative. Agreed? You find the antiderivative, you put it here, you put that bar here, and then you put the a and the b here, right? And then you plug in b and you plug in a and you subtract. Okay, I want you to do that. Now, b and a are not, I'm not giving you what they are. So your answer should be an expression that has b's and a's in it. You think you can do that? Take some time to do it. Y'all can talk to each other, but try and, see if you can't get that done.
Yeah, when we switch it to 10.
Yeah, that does switch, but you haven't integrated it yet.
Yeah, that's what
Yeah. I want you to integrate that.
There's no way to split that.
Y'all doing anything over here? Okay, good. That's what I want to see. Yep. Be right there. Yes, you're on the right track. Go the other way. Go the other way on this.
Really?
Yes, because remember, whatever u is, the derivative of it is going to be in the new integral. So if you put the x here, the derivative of it's going to be 1. No? Yeah, but hold on, because this right here would be these two together. Ultraviolet minus voodoo,
Oh,
right? And that's more complicated.
right. Actually, can I also turn this in? I didn't put them on there, but I boxed them on the.
Okay, okay. Yeah, yes. Is that x? Yes, that's the way you want to go on that. Okay, your question?
I was just gonna ask if we should use the what is this method called? Ultraviolet.
Yes, integration by parts.
Yes.
Yep, you should be using integration by parts there.
And would I make u x u to x?
You got to make it one of those, right?
I can make it one.
Well, if you made it the whole thing,
Well, not dx, but like just x u to x.
x e to the x, you could, but I think it'd be much harder. Instead, just pick one of those, either x or e to the x.
Whichever one would be easier.
Whichever gets easier in the new integral. Yeah, x for the u. Y'all finish it? Yeah, okay. All right. Okay. All right, I think that's sufficient time to at least get you thinking. Integration by parts, I was hoping that would have been something you would have recognized right away. So you're trying to integrate this. So I'm going to do it as its own problem over here. You let u be x, dv be e to the x dx. And then du is dx and v is e to the x. So then your new integral becomes ultraviolet, so x e to the x minus integral, and then these two, e to the x dx. And then the antiderivative of e to the x is just itself. So what I would say here is that this is x e to the x minus the antiderivative of that, which is just e to the x. I don't need a plus c because this is a definite integral. Then I put a here and b here. Right? Then if you plugged in b, bless you. If you plug in b into this, you get b e to the b minus e to the b. And then here you get a e to the a minus e to the a. Right, that's where we would be. All right, we'll need this later. I just wanted to give you that to work on real quick. All right, are we ready to move on? Oh yeah, all right, all right, all right. We're going to start 6.6. All right, improper integrals. Improper integrals. Now, let me warn you ahead of time that to do this, to do what we're about to do, you have to be comfortable with taking limits, which is something you did in Cal 1. And I will also be implementing L'Hopital's rule. All right? So there are several things that you need to be able to recall here from Cal 1. And in my class I had yesterday, we did this section, and about, I don't know, maybe a third to half the class had forgotten what you do when you see certain things with limits. So I sent my class yesterday a link to some of my Cal 1 videos where they could go back and watch me lecture on L'Hopital's rule. But I think in Cal 1, I usually spend like 2 days on L'Hopital's rule. So, I'll send you all the same thing.
So you're saying like all of them are going to be applicable L'Hopital's that we're going to be doing?
Not every single one of them, but we'll need it. See, what you need to remember from Cal 1 right now are what are called the indeterminate forms of limits. So like, when is it that we have bad situations? If we're taking a limit and you ever get 0 over 0, now realize this is when I'm taking a limit. If you ever get 0 over 0, that's bad, right? And so we have to do something. And we can use L'Hopital's rule on that. If you ever get like infinity over infinity, then you can use L'Hopital's rule on that. But those aren't the only indeterminate forms. There's also, if you ever have infinity minus infinity, then that is not 0. That you have to do something with it. If you ever get 0 times infinity, that again is not 0. That is indeterminate, so you have to do something. All of these indeterminate forms, you need to, if they show up, and you need to be able to deal with them. So just be forewarned, you might have to go back and review some of this if you don't remember it, all right? Now I'll try and cover it as much as I can as I go through the problem, but I can't possibly in 10 minutes, do what I would normally spend 2 days on, all right? All right, improper integrals. So there's actually 2 types of improper integrals. Today we're going to talk about infinite intervals, and next class we'll talk about the other one, all right? So type 1 and type 2. So up to this point, and actually we just did this last class, the definite integral, right? So it's not like we spent a whole lot of time on it, but we've only dealt with integrating over a closed interval from A to B. What we're going to do now is we're going to let that interval become infinite. And that means we're going to have integrals that are going to fall into one of these three categories, I guess you could say. We're either going to be integrating from A to infinity, or we're going to be integrating from negative infinity to B, or we're going to be integrating from negative infinity to infinity. So let's try and get our heads around what this is doing geometrically. So I'm telling you, notice that the limits of integration are no longer fixed numbers. They're the infinity symbol. Here we have a fixed number, but here it's infinity. Here it's infinity, here it's a fixed number. So let's see if we can't get an idea of what this means geometrically. So let's take a look at this first one. What if we want to do an integral, definite integral from a to infinity of some function? Now what this means is that we want the area, right, below the graph, or between the graph and the x-axis, starting here at A, and ending where? Yeah, so never ending, right? Infinity is not a number, right? Infinity is an idea. So we're trying to figure out the area underneath this function if we were to go forever this way. And so things start to become a little bit weird, all right? Like, do you think it's possible that we could even get an answer that would be like a nice number? Or do you think that the answer would be infinity? I mean, think about this. Look at this graph. Do you all agree we have some area here? So we're going to get a positive number, right? Now, if I keep going here, like let's say I stopped at 6, right? That would give me a number, right? I would have a number. But if I go to 8, it's going to be a little bit more, right? If I go to 10, it's going to be a little bit more. If I go to infinity, is it going to be infinite? You know what I'm saying? I'm trying to get you to think, like, what is your intuition telling you? That if I go forever, I mean, is it going to be, I always like to envision like a cup, and we're trying to fill this cup up, right? We start putting stuff in it, and as we go out, we keep putting stuff into this cup, right? Is this cup going to overfill? If we keep going forever, will the cup overfill or not? Yes, I'm hearing yeses, I'm seeing nods, I'm seeing dazed and confused looks. So this is a question mark, okay? Right now it is a question mark, but it should trouble you a little bit. if we get an answer, like let's say we do this problem and we get the answer 2, then that means that even though this goes forever and we have some area the whole way, it's not ever getting over 2. And that should cause a problem. I think intuitively it does. So let's see what happens. Now, what are we going to do when we see an integral like this? What are we going to do? Well, if this was a and b, we would just do it, right? If it was a and b, we would do it. But we don't want this to be b, we want it to be infinity. So what we do is we replace the b with t, all right? And so with this limit's not here, that we could do, right? That would be like from a to b. But we replace it with t so that we don't confuse it with b. And then what we do is we figure out what the answer is here. And then after we do that, we take the limit and we let t go to infinity. So what we're doing is we're picking some arbitrary value of t out here. We're saying, what's that area? And we're going to get a formula for it because our answer, when we do this, our answer is going to have a t in it because we don't know what t is. And so once we get that answer, we're going to then let t go to infinity. And that's going to make that point just, run out that direction forever. Yeah? So,
Are we still going to subtract the integral?
yep, we're still going to subtract. Yep, we're going to do. So the a is going to be just like normal, but that infinity is going to be the t, and we're going to take the limit. Now, if we do the other way, right, the integral that goes from negative infinity to b, this is what it looks like. So you have, here's b, but this time we're going from negative infinity, which is way over here, right, and we're coming this way, and we're stopping at b. But it does go that direction forever, right? So it's the same concept, just flipped over there. And it still brings up the same question, like what happens, right? Do we get a number? Does it become infinite? Look how this changes, right? We leave the b alone, we replace the negative infinity with t, and then we take the limit as t goes to negative infinity. Y'all see that? So to do these problems, these improper integrals, type 1, infinite intervals, we have to be able to do limits. And then the last case that we could see would be if we wanted to find, I should mention this. Remember in Cal 1 that when you took limits, sometimes you got an answer does not exist? Do you remember ever taking a limit and it's like the limit does not exist? And sometimes it did exist. If these limits exist, we say the integral is convergent. So this is new terminology. If you're doing this problem right here, you do this and then you take the limit and you get an answer, then we will say the integral is convergent. All right? If the limit does not exist, then we will say that the integral is divergent. So these are new words for us. Think of convergent as going to something, right? Things converge, it's going to something. So think about it as like that area is going to something, as opposed to divergent, which means the area is not going to something. What I mean by something is a number. Yes?
So in reality, basically what we're doing is like the integral is the area, and the limit is what y value it's approaching. So we're looking at what y value the area is approaching.
It's not the y value. The limit is actually the limit of what the area is approaching.
Yeah.
Yeah, not
Like
the
what-
y value
what
of the
value
function.
Oh, okay.
Because look, in that picture I just showed you, would we all agree that the function is approaching 0?
Yeah.
Like the function is approaching 0 as I go out this way. But that doesn't mean that the area is approaching 0 so they're related but two different quantities. One of them is what the function is approaching, the other one is what the area is approaching. All right? Okay. So convergence and divergence. We're going to talk more about this as we do the problems. We'll use the language. Hopefully, my class yesterday had some trouble with the convergent and divergent idea. Let's see how y'all do. Now, lastly, if we want to integrate from negative infinity to infinity, That means we want the area under a function on the totality of the entire real number line, the entire area underneath the function. Then the way we do it is we break it up into two integrals. And the first one goes from negative infinity to a, and the second one goes from a to infinity. So it's kind of like what you do is you say, I've got to go that way forever and that way forever, so I'm just going to pick any point I want in between. Anything I want. A. And then I'm going to split this up. I'm going to find that area. That would be this integral. And then from a on to infinity would be that integral. Does that make sense? And that was that property that I showed earlier where you had, if c is between a and b, then you can split it into two integrals. So as long as I pick a number between negative infinity and infinity, which is any number, right? Then I can split it up into two pieces. Now, in order for this to converge, this is important. In order for this to converge, both of those have to converge. If one of these diverges, the whole thing diverges. All right, that's it. Let's do an example. We have the integral from 1 to infinity of 1 over x squared dx. I'm going to show you the graph of this function, all right? Even though you don't need the graph to do the problem. This is what it would look like if you graphed it. This side would go up like this, and this side would also go up like that. You would have a vertical asymptote at 0. Is that obvious to you? That if we plug in 0, it's undefined? So we'd have a vertical asymptote here, and then if you go out both directions, you get 0. You head to 0, right? So if the integral wasn't here, and I asked you, what does that function do as x goes to infinity? Would we all agree that that goes to 0, right? If I ask you, what happens to this function if x goes to negative infinity? It goes to 0, right? All right, but that's not what we're asking. It's just that's why we get the horizontal asymptote like this. So what we're looking for now is the area starting at 1. So if I plug 1 into that function, it spits out 1, right? 1 here, 1 here. That's not really relevant, but I'm looking for this area that goes this way forever, right? That's forever. And the question is it converging to a number or is it diverging? So let's run through the method. This looks like this one, integral a to infinity, right? That's what that looks like. So what I'm going to start with is a limit. I'm going to let t go to infinity, and I rewrite the integral. I leave the 1 as a 1, and I replace infinity with t, right? And then I have 1 over x squared dx. Now you get to take the antiderivative, don't you? You get to take the antiderivative. Now, the limit is still out here, right? So I'm going to write it down because I have not let t go to infinity yet. And I will always write the limit. I will continue to write the limit until I actually let t go to infinity. So yes, I'll have to write a lot of stuff. All right, so there we go. I'm going to use a bracket. The antiderivative of 1 over x squared is negative 1 over x. So that's really like x to the negative 2, and then the antiderivative of x to the negative 2 is negative x to the negative 1, and then blah, blah. We've done that enough? Yeah? Okay, then we put the evaluation bar here. I put a 1 down here and a t down here. So that's basically from last class, right? Now what I'm supposed to do is plug in this number, right? And then subtract what I get when I plug in this number. So I'm going to write that next. And I'm still going to throw the limit out front. Any questions? So that's my standard thing I like to do, 2 sets of parentheses so I can plug in the t and plug in the 1. So when I plug in t for x, I get negative 1 over t. And when I plug in 1 for x, I get negative 1, right? Negative 1 there. At this point, I think I'm ready to let t go to infinity. So let's let t go to infinity. What happens to this right here if t becomes infinitely large? That goes to 0, right? Now, is it 0? No, it heads to 0, doesn't it? So this is going to get smaller and smaller and smaller. So in the limit, that goes to 0, right? And then minus 1 plus 1, right? Which is 1. It's convergent. It's convergent because it heads to a number, right? Did this limit exist? Did that limit exist? Yes, therefore it is convergent. Now, what is it saying to us? What is the answer 1 actually saying? Yeah, so if you were to start to figure out what this area is, right? Then if you could, see this is almost theoretical, if you could keep going forever, right? It would converge to 1, which means that the area out there forever, like that whole area forever, is 1. Yeah, I know, that's why it's a little troubling. Hold on a second. So like if I went to 10 here, right? Let's say I stopped at 10 instead of infinity, right? If I did that, then this would have been 10, right? And then this would have been 10. So I would have had negative 1/10 right there. Negative 1/10 plus 1. So that would have been 9/10, wouldn't it? 9/10? 0.9? Agreed? If I would have stopped at 10, it would have been 9/10. Now, what if I would have stopped at 100? Let me make that 100 instead of 10. Then this would have been that. And then this would have been 99 over 100, which would be 0.99.
Oh, yeah.
Almost 1. Now, if I went to 1,000, this would be 1,000. This would be 999 over 1,000, which is 0.999. Right? Do you kind of get what's going on here? The further out I go, the closer I get to 1. If you could go forever, which is conceptual, right? Then you would have 1. Thing is, you can't ever go all the way forever, but the further you go, the closer you get to 1. You will never exceed 1, though. That's the key, though. You'll never go past 1, ever. Ever. Because, I mean, take this and take this out, however many digits you have here, right? Isn't this always going to be like a bunch of 9s over that? But we'll always have one more digit down here than up here. So this is going to be like 0.999999999, maybe 30 9s out there. That's still not 1, right? Okay. Convergent, that is a convergent integral. Let's try another one. Yes. Oh, wait, you had a question. Sorry, I never came back to you.
It's fine.
You sure?
Yeah,
You're happy?
yeah, no.
Okay. Oh, you didn't say that. I put those words in your mouth. Sorry. What?
We don't have to, because that was just the right side.
Yeah.
Okay, but if we needed to do, we don't need to do like what, the whole thing.
Well, this is asking us just to find the area from 1 to infinity.
Oh, okay.
Okay, if they would have wanted us to do 2 to infinity, then we would have gone, If we want the whole thing, right, both sides forever, that's actually very problematic. Do you know why?
Set it at 0.
Could you go from 0 to infinity? Why couldn't you go from 0 to infinity? Because the function is not defined at 0, right? So you think about the area here. If I were to go from 0 instead, you would have this area forever this way, right? But you would also be including this area, right? And oh crap, what's happening right there? You have a vertical asymptote shooting up that way, right? So that's a problem, right? Not only is it going to infinity, which is a limit, right? But you also have a place, if you're including 0, where your function is undefined. So guess what type 2 improper integrals deals with? This situation where you have division by 0. So we will next class be able to talk about getting this area right here. So stay tuned. Next class. All right, let's do this one. All right, so look at this function 1 over x. That's not very different than 1 over x squared, is it? I mean, in terms of this still goes to 0, right? 1 over x goes to 0. If we go from, we're still going 1 to infinity. So if we go out to the right, it's going to basically behave the same way, right? So our graph would look like this. The graph is a little different for 1 over x. It does this, but on the other side it does this. Now that doesn't matter what's going on the other side, because I still only want to look from 1 to infinity. At 1, it's still 1. And so we're looking for this out this way, right? The thing about this function, though, is that 1 over x and 1 over x squared do have a pretty fundamental difference between the two of them. Like 1 over x squared, that's going to get small very fast. Would you agree with that? Faster than 1 over x does. Let's see if that has an impact on the area. So first start this out, limit t goes to infinity. I leave the 1, I replace the infinity with t.
Does it being odd have any influence? Like,
In this case, it's not the fact that it's odd, because this is an odd function, but that's not why it's going to do what it does. It's because of what its antiderivative turns out to be. So we have this, right? And now we actually find the antiderivative, so I rewrite the limit. My antiderivative is natural log of the absolute value of x, right? Then my evaluation bar, 1 to t. And then that's the limit. T goes to infinity. 2 sets of parentheses. And plug in t, plug in 1. So natural log of absolute value of t, and the natural log of absolute value of 1. At this point, I'm going to let t go to infinity. Bless you. What is natural log of t if t is going to infinity? What does natural log of infinity mean? Like, what's going on there? Is it infinity? So why is it infinity? You have to understand what the natural log function looks like. Okay? To do this, you need to know what natural log looks like. So natural log of t, or natural log of x if you want, looks like this. Right? It's an asymptote there. The natural log function does not exist over here because you can't plug a negative number into a natural log function. Although with the absolute value it does change things, but we're only looking from 1 to infinity, right? So if we are looking at the natural log function here and we're saying plug infinity in, what we're saying is what is the natural log function doing if we start going out to infinity? So what does it do? It's getting bigger. It's becoming infinite, isn't it? So that function is approaching infinity. So this is going to infinity. Now that is not enough for us to say it diverges. Because if this says minus infinity, then we have perhaps an indeterminate form. But we got lucky because natural log of 1 is 0. So this is infinity minus 0. and that's infinity. So this limit is going to infinity. So we would say that the limit doesn't exist because it's not going to a number, because infinity is not a number. So because it's going to infinity, we will say that this diverges.
So would you have to point out that like limit does not exist?
You would have to, you would need to show that this is an infinite, that this is going to infinity. Okay? And then once you do that, you can conclude that it diverges. See, the last problem we got what? 1? And so we said converges. And it converges to 1. You could actually say this is actually converging to infinity. It's saying that the further we go out with this graph, right, it's getting more and more area. So like if I went to 1/10, I would get an area. But if I went out to, not 1/10, if I went out to 10, I'd get a certain area. If I go out to 100, I'm going to get more area. But it's not like the 0.9, 0.999. It's like it just keeps like overfilling it. You know, maybe it's like 2. The area is like 2 here, and then it's going to become like 2.5, and then maybe it's like eventually you'll get to 3, and then eventually to 4, and then eventually to 5, and it just keeps getting bigger. Yes?
I think that's a pretty drastic change, though, from infinity, and then like the other area was 1
Mhm.
we got. So
And all we did was change the power from
yeah, like,
1 to, right, this power on x is 1, and the one on the before was squared.
so I don't know.
Yeah, that has a pretty big impact on things.
Due to like the scale we're looking at, like we're only looking at like 1 to small numbers versus this one. If we do say a trillion, like you said, it's gonna eventually get to 2 to 3.
Yeah, eventually. So, but with the 1 over x squared, what's crazy about that one is you can go to a trillion, into a trillion, and it's never going to get past 1. Where this one, what it all comes down to is the fact that this function is kind of decaying as you move out to the right, right? It's headed to 0. It's just not headed to 0 fast enough. And so those areas accumulate fast enough that it's overfilling the cup. But the 1 over x squared decays fast enough that those areas don't overfill the cup. I think this is always a problem with your intuition, because they both have the same basic premise. You are adding up an infinite amount of area, but you're getting 2 different answers, one of them being a number, one of them being infinity. That should be a problem. And that's why in the real world, okay, you cannot always count on your intuition. You know, I know civil engineers in here, like majors, right? There's a lot of civil engineering majors, mechanical engineering majors, right? You can't just go out there and be like, yeah, that beam looks strong enough. You know, you can't trust your intuition. You have to understand what's going on. And if the mathematics tells you it needs to be this, you have to trust it. You know what I'm saying? Of course, intuition's important. But when it comes to things like building bridges in airplanes, if something is going against your intuition and the math is showing you one thing, you have to kind of trust the math. All right. Remember that bridge that fell in Florida a couple of months ago? Yes? Killed a couple of people, too. I haven't heard a definitive reason why. I've only heard what I've read on YouTube, which of course is true, or what I've seen on YouTube. But I believe that it had to do with the fact that they lifted it. Y'all know what bridge I'm talking about? They built it on the side of the road. They lifted it up and put it over the road. And from what I heard is the original plan, they were supposed to lift it from 2 different points. And because there was like a pedestrian walkway, they lifted it from a different point. And so when they lifted it in place, and they used post-tension cables. You know what post-tension is? Like, they're like big wire, steel. They're not rods, but they're like wire. And then they pull them in the concrete, and it compresses the concrete. They build foundations of homes like that. So when they post-tensioned it, because the pickup point was at a different place, the load was not accurate, like it wasn't what it was supposed to be. So then when they put it in place, they